Imagine you're in space far from any gravitational field. You push a ball for a short time and let go. Think about the motion of the ball after you release it. After you release the ball and no longer push it, is there a force acting on it? What do you think?
I think there will be no force since it says you're far away from any gravitational field.
Okay, so now imagine the motion of the ball. How does it move? Can you describe the motion of the ball in your own words?
Well, the ball is probably going to move in the direction in which you throw it.
That's very good. Would it go in a straight line or would it go in a curved line, you think?
A straight line?
Very good. So why do you think it would be in a straight line?
Because there's no force acting on it.
Okay, so in order for it to change direction, you think there should be a force acting on it, right?
Yeah.
Okay, so that's really, really good. Very good. So the ball would not stop, right? Unless a force acts upon. Now try to imagine if you want to mark the location of the ball at every second, what dot per second? What do we see?
The dots are evenly spaced out.
Okay, very good. So it would be a dot, 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 right? Something like that. Okay, so this is something that we call motion maps. Motion maps are diagrams that show the position of an object as a function of time at equal intervals. So it could be any type of intervals, but at this time in this part of the book, we are going to imagine 1 dot per second, okay?
Okay.
So what do you think about the motion of this object? Let's say the object is moving and this is the motion map of an object. Let me mark it for you so you can see it. This is the motion map of an object. What can you say about this motion?
It's moving like the ball in space because it's moving at an equal pace per second.
Very good. So just like the ball that you release in space, equal intervals. So this object is moving with a constant speed. Very good. So that was a very good description of this motion. So now look at these two objects, object 1 and object 2. This is a motion map of object 1 and this is motion map of object 2. Which one do you think is moving faster? This is a little bit hard for some of our friends, but give your own description and description of this motion and tell me which one is going to move faster.
Object 1 because they're closer together.
So object 1 is moving faster, you think?
I think so.
Oh, okay. So let's just see for first 5 seconds, which one moved more. So this is object 2 in the first 5 seconds, and this is object 1 in the first 5 seconds. Which one moved more?
Object 2. So object 2 is going faster.
It's going faster. And it doesn't have to be 5 seconds, right? It could be any second, right? In 1 second, object 1 has moved this much, but object 2 has moved this much, right? Okay. So in order to understand the motion maps really, really well, I propose an experiment here. So for this experiment, you need to have some soft objects like pom-poms or cotton balls, and we're going to drop them on a soft surface. So if you have rocks or Legos or something like that is hard, and if you drop them on a hard surface, they're going to bounce off and they're not going to stay in place. So soft objects are much better on a soft area. What we're going to do is that we're going to get a handful of pom-poms and we're going to drop them every second as we walk. So in the first experiment, what we're going to do is that we're going to have a handful of experiments, handful of pom-poms, maybe 5 or 6, and we're going to walk very slowly at a slow pace, and we're going to drop 1 pom-pom per second. Can you describe, can you imagine it first? We're going to do this experiment, but it's this experiment, but imagine it first. What would you see if you look back?
Well, since you're dropping them every second, they're going to be evenly spaced out.
Very good. And what can you say about the spacing between them if you're moving very slowly?
They're going to be closer.
Closer together. Right. So if you actually do this experiment, it's probably going to clarify this much better. Now you walk a little bit faster. If you walk a little bit faster, you're going to see more distance between the pom-poms. And if you walk even faster than that, or if you run, the distance between the pom-poms are going to increase even further. Okay, so this is going to clarify a lot of issues that people have in the motion maps. So another experiment that you can do is that if you stand in place and drop the pom-poms as a function of time, they're going to accumulate like that in one location, right? But in motion map, when we want to show an object that is not moving, we are going to just stack them on top of each other. Can you please look at this motion map and tell me how long this person, standing still? Can you count the seconds for me? Oops, let me get a different pen. I don't like this pen. Okay, go ahead.
1, 2, 3.
Very
3
good.
seconds.
For how long was she moving for?
1, 2, 3, 4.
Very good. 4 seconds. So this is how you read the motion maps. But the thing that we're going to get from this experiment is that if the dots are closer together for the motion map, it means that the object is moving slower. If they're farther apart, it means what?
They're going faster.
Yeah, the object is moving faster. Very good. And if they are stacked on top of each other,
then there's no motion at all.
No motion at all. Very good. So let's keep experimenting, but this time in our imagination. Think about the motion map of a skydiver as she jumps off the plane. What do you think is happening? Or you can kind of see it in this motion map, but can you please describe the motion map for me for the skydiver?
So in the beginning, the dots are like more close together.
Mm-hmm.
So it's probably going like a little bit slower in the beginning.
Very
and
good.
Then the skydiver starts to speed up as they're going down.
Right. So the distance between the dots increases as she falls down, right? So why do you think that happens? What is the difference between this motion map and the motion maps that we just described before?
Well, this one, the dots are differently spaced out.
Mm-hmm. But
between
why
per
do you
second.
think they are differently spaced out? Or why do you think this person is actually moving faster and faster as a function of time?
Because there's a force acting on it.
Oh, very good. Okay, so what kind of force is that, do you think?
The gravitation.
Yeah, so this is the gravitational force. And if I have to draw it, what would be the direction of that force?
Down.
Downward, right? So you can kind of see that now if you look at the force if you look at the motion of this object and is speeding up, and this object is moving downward and is speeding up in that direction, there must have been a force that is acting on this person downward, right?
Yeah.
What does she need to do to slow down, you think?
She has to pull her parachute out.
Right, so she can open a parachute, right? So if she opens a parachute, what is that going to do, you think?
It's going to make her slow down.
Right, but why does it make her slow down? Do you remember there was a force acting on her body downward? So why does the parachute actually slow her down?
Because there's a force acting the other way. The
other way, right? Upward. So this could be, what kind of force is that, do you think? That upward force. What kind of force is it? Who's applying that force? What is applying that force?
The parachute.
Right. So the parachute itself causing the air resistance, right?
Mm-hmm.
Or air drag. Okay. So this blue force is what?
The gravitational force.
Yeah, very good. Force of gravity, gravitational force. Very good. So now what do you see in the motion map?
It's moving at a steady pace.
At a constant speed, at a steady pace. Very good. So can you describe the relationship between what we see in this force diagram? I'm going to call this a force diagram. What do we see in this force diagram and what we see in terms of the motion map?
If the air resistance and the force of gravity are equal, then
that's a good guess.
They're
good
going
job.
to move at a constant speed.
Very good. So do you remember the ball that we released in space?
Yeah.
That ball was not experiencing any force at all, right?
Uh-huh.
But in this motion map, there is force of gravity and there is air resistance, and our object is still moving with a constant speed. What can you say about these thought experiments that we have done? There was an object that is moving in space and experiencing no force at all. And we have objects that are experiencing balanced forces that are in opposite direction, but they're equal to each other, right?
The forces might cancel each other out. So it's like having no forces on it at all.
Oh, very good. Very good. So I'm going to give you another question here. So let's say for any reason, let's say this air resistance was a little bit more than force of gravity. What do you think is going to happen to this object as it moves down?
Maybe it will slow down.
It would slow down. Very good. Why do you think that is the case? What would be a leftover force on this object? Let's just get a green pen the leftover force on this object, let's say, let me just make this air resistance a little bit bigger, okay? Let's say this air resistance was very large compared to the force of gravity, okay? What do you think the leftover force would be on this person? The leftover force or net force, would it be upward or downward?
Upward?
It would be upward, right? So if the person is moving down and is experiencing a force upward, it would slow down. Very good, as you said before. So that's very good. Good job. All right. So let's explore a little bit more. These are some examples of forces that are canceling each other out, right? You see the blue force is equal to the red force, right?
Yeah.
And that is canceling each other out. What can you say about the second scenario where you have a blue force to the left and you have a red force and an orange force to the right? Are they canceling each other out?
Yeah, because the red force and the orange force,
Addition of those two.
well, since they're like both added together, they cancel out the blue force.
Because they're in the same direction, right?
Yeah.
So addition of the red force and orange force would be equal to the blue force, and they're going to cancel each other out. So we're going to call this also a balanced force. So if you have a situation where the forces are balanced like that, what do you think is going to happen to the motion of the object?
It's going to move at a constant speed.
Constant speed. Very good. So objects that are moving at a constant speed may not experience any force at all, or they might experience balanced forces, right? Okay, so let's say we have these blue forces. I'm going to draw one. I'm going to balance one of these. I'm going to balance the one on the right. I'm going to draw something. Ooh, I don't like this one. Let's get a pen. I'm going to draw a force that balances that one out. So something like that. Do you agree? Do you want to draw one for the middle one? Let's say we're going to go to the yellow. How far down should we go? Do you want to draw one?
Okay.
Okay, so... Oh, that's very good. Yeah, up to there. Good job. What about the one on the left? Let's draw one. Do you want to do a combination of forces on that?
Okay.
Okay, so let's say you have a green force. Oh, very good. So that's a green force. And then you want to add what color?
Red.
Okay. And then we just have to guess. It doesn't have to be exact. You can actually use a ruler. That's pretty good. I would agree with this. Very good. Awesome.